Good day to all. This is my third lecture on molecular orbital theory, and in today's class I'll be discussing about the molecular orbital diagrams of homonuclear diatomic molecule. This class has three learning outcomes. Number 1, filling of electrons in the molecular orbitals of homonuclear diatomic molecules. Number 2, calculation of their bond order to know the number of covalent bonds between the combining atoms and to predict their stability. And number 3, discussion upon the magnetic behavior of all such molecules. We'll begin our discussion on homonuclear diatomic molecules by taking the simplest case of hydrogen. Hydrogen molecule is formed by the overlap of 1s atomic orbitals of two hydrogen atoms having one electron each. From the overlap of these atomic orbitals, two molecular orbitals are generated. One is the bonding molecular orbital, which is designated by the symbol sigma 1s, and the other is the antibonding molecular orbital sigma star 1s. In this molecule, we have total of 2 electrons which are to be accommodated in these orbitals. Now, since the bonding molecular orbital is having lower energy, so both the electrons will enter into the sigma 1s orbital. This is as per the Aufbau principle and Pauli's exclusion rule. Hence, the molecular orbital configuration of hydrogen molecule will be sigma 1s2. The bond order of this molecule can be calculated by the formula, that is Nb minus Na upon 2, where Nb stands for number of electrons in the bonding molecular orbital and Na for number of electrons in the antibonding molecular orbital. Now in this case, bonding molecular orbital is having 2 electrons and antibonding molecular orbital is having no electron. So the formula will be 2 minus 0 divided by 2, which comes out to be 1. What does it mean? What does this 1 mean? It means that there is a single covalent bond between the two hydrogen atoms of hydrogen molecule. And since the bond order is greater than 0, so hydrogen molecule is stable and it exists. Now let us comment on the magnetic behavior of this molecule. This molecule is having both the electrons paired and hence it is diamagnetic in nature. Now let us talk about the He2 molecule. He2 molecule does not exist, and the reason for it is that its bond order is coming out to be 0. Now He atom is having the electronic configuration of 1s2. Now 2 He atoms will have 4 electrons, and these 4 electrons will be arranged in sigma 1s and sigma star 1s orbital, 2 in each. Thus, there will be a stabilizing effect of electrons in the bonding molecular orbital, and that effect is cancelled by the same number of electrons in the antibonding molecular orbital. Hence, the net effect will be 0 and this molecule will have the bond order 0 and it will not exist. Now let us take another example of helium 2 plus ion. Helium 2 plus ion is formed by the combination of helium atom with helium ion. Helium atom is having the electronic configuration 1s2 and helium ion is having the electronic configuration 1s1. Upon the combination of these two orbitals, two molecular orbitals are generated named as sigma 1s and sigma star 1s. Now we have to fill the 3 electrons in this molecule ion, and 2 electrons will enter first in the sigma 1s orbital and the next electron will go to the sigma star 1s orbital. Now let us calculate the bond order. Bond order will be 2 minus 1 divided by 2, that is 0.5, which means that this molecule ion exists, but its stability is less as compared to hydrogen molecule whose bond order is 1. The stability is directly related to the bond order. Higher the bond order, higher will be the stability. On the similar lines, we can draw the molecular orbital diagram of lithium. Lithium atom is having the electronic configuration of 1s2 and 2s1. Now 3 electrons are present in each atom and the total number of electrons in lithium molecule will be 6, we have to accommodate the 6 electrons in these 4 molecular orbitals, which are sigma 1s, sigma star 1s, sigma 2s and sigma star 2s. Now these 6 electrons will again be filled by following the Aufbau principle and Pauli's exclusion rule, and all will be in the paired state. So this molecule is diamagnetic and bond order will be 1, which is calculated by the same formula. Number of electrons in the bonding molecular orbitals are 4 and number of electrons in the anti-bonding are 2, and hence the bond order will be 1. Beryllium molecule Be2, it is unstable, it doesn't exist, and the instability is on the same lines of bond order similar to that of helium molecule He2. Now let us talk about the next molecule, that is boron. Boron atom is having the electronic configuration of 1s2, 2s2 and 2p1 since the atomic number is 5. So one atom of boron is having 5 electrons. So 2 atoms will have 10 electrons, and then these 10 electrons have to be filled in the molecular orbital skeleton of this molecule. Now to draw the molecular orbital diagram of boron 2, we have to follow the nitrogen type or lighter nuclei type case. In the lighter nuclei type case, the pi 2px and pi 2py orbitals are placed below sigma 2p z orbital. Whereas in the heavier nuclei type case, the sigma 2pz is placed below. So we have 10 electrons in total that has to be filled in these orbitals. Now while filling the electrons in these orbitals, molecular orbitals will follow all the 3 rules. First is Aufbau, second is Pauli's, and here we'll also follow the Hund's rule of maximum multiplicity. Now when we are filling the electrons in the degenerate levels having the same energy, then while filling them, we have to first make them half filled and then the pairing will begin. Now 8 electrons will be filled in the sigma 1s to sigma star 2s orbital in the similar fashion, but the next 2 electrons will be going singly in pi 2px and pi 2py orbital. Why they have gone singly? Why pi 2px is not having 2 electrons? Because this is against the Hund's rule. Okay. So we'll fill the electrons in this manner, and now we can see that 2 unpaired electrons are present in this case. So this molecule is paramagnetic in nature. We can calculate the bond order by the same formula, that is for this molecule it will be 6 minus 4 by 2, that is equal to 1. So the bond order is 1 for boron molecule. Now let us move to the important case of nitrogen. Nitrogen is a lighter nuclei. Pi 2px, pi 2py is placed below sigma 2pz orbital. Now this nitrogen molecule is formed by the combination of 2 nitrogen atom. Nitrogen atom is having the atomic number of 7 and its electronic configuration is 1s2, 2s2 and 2p3. 2 nitrogen atoms overlap to form nitrogen molecule, and total of 14 electrons are there that has to be filled in the molecular orbitals of nitrogen. We'll start the filling from sigma 1s and we'll go up to sigma 2p z orbital. So up to sigma 2pz, 14 electrons will be filled. Now let us calculate the bond order for this. Bond order is 10 minus 4 divided by 2. What is 10? 10 is the number of electrons in the bonding molecular orbital. Now let us count where these 10 electrons are placed. 2 in sigma 1s, 2 in sigma 2s, and rest 6 in pi 2px, pi 2py and sigma 2pz. And 4 electrons in antibonding molecular orbital are present in sigma star 1s and sigma star 2s. So on calculation, the bond order for this molecule will come out to be 3, which means that there are 3 bonds 1 sigma 2 pi between the nitrogen atoms in this molecule. Now let us take a look on the magnetic behavior of this molecule. This molecule is diamagnetic in nature. Why? Because all the electrons in the molecular orbitals are in the paired state. There is no unpaired electron in this molecule, and hence it is diamagnetic in nature. Now, in order to predict the bond order magnetic behavior of the ions of nitrogen, we will see the nitrogen 2 plus ion. Nitrogen 2 plus ion means a 13 electron system. The 13 electron system, why? Because this N2 plus ion is formed by the loss of one electron from the nitrogen molecule, which is having 14 electrons, and this one electron will be lost from the highest occupied molecular orbital, that is HOMO of this molecule, nitrogen. What is HOMO? HOMO stands for highest occupied molecular orbital. Whenever we are removing the electron to form the positive ion, that has to be removed from the highest occupied molecular orbital. And here the highest occupied molecular orbital is sigma 2pz. So to form the N2 plus ion, we will be removing the electron from there, and then we will be calculating its bond order, its magnetic behavior, and all those properties. Bond order for N2 plus will be less than that of nitrogen molecule, because we are removing the electron from the bonding molecular orbital. Whenever the electron is removed from the bonding molecular orbital, the bond order decreases, and whenever it is removed from the anti-bonding molecular orbital, bond order increases. So N2 plus ion is having this electronic configuration. It is paramagnetic in nature because the sigma 2pz orbital will be singly occupied and one unpaired electron is present there, and as I said earlier, it is less stable. Its bond order will be lesser than that of N2 molecule, and it is 2.5. So it has less stability than N2 molecule. Now let us take up the case of N2 minus ion. How N2 minus ion will be formed? N2 minus ion will be formed by adding one more electron to the nitrogen molecule. So nitrogen molecule is having 14 electrons. We have to add one more electron to that same system. We will be adding one more electron, so the system will have now 15 electrons, and these 15 electrons will be filled in this molecular orbital skeleton. So the 15th electron will go into the pi star 2px orbital, isn't it? It will be entered in the lowest unoccupied molecular orbital, that is pi star 2px. What is lowest unoccupied molecular orbital? The molecular orbital which is vacant and it is lowest in energy. So here we are having three vacant orbitals. The sigma star 2pz orbital is having higher energy, and pi 2px, pi 2py are having same energy. So the 15th electron will enter in pi star 2px orbital, and on the same lines we will be writing the molecular orbital configuration of this ion, and we will be calculating the bond order and magnetic behavior. The N2 minus ion will also have the bond order of 2.5. You people also calculate in your notebook, and you will also notice that it is paramagnetic in nature because it is again having one unpaired electron, and where this unpaired electron is present? In pi star 2px orbital. On the same lines, we can write the electronic configuration of N2 2 minus ion, and we can calculate its bond order, and we can predict its magnetic property. Now let us move to the last molecule of today's class, that is oxygen molecule. Now this oxygen molecule differs from the nitrogen molecule in only one aspect, that is the placement of sigma 2pz orbital with respect to the pi 2px and pi 2py orbital. And the other difference between the two is that nitrogen was having 14 electrons and it will have 16 electrons. oxygen atom is having 8 electron. 2 oxygen atoms matlab 16 electrons, and these 16 electrons have to be accommodated in the molecular orbital skeleton of this molecule. We'll start filling the electron from sigma 1s and we'll end up with the last electron in pi star 2py. The 16th electron will enter in the pi star 2py orbital, and then we will calculate its bond order. The bond order will have the formula 10 minus 6 divided by 2. What is 10? Number of electrons in the bonding molecular orbital. And let us see where these 10 are present. 2 in the sigma 1s, 2 in sigma 2s, and remaining 6 in sigma 2pz and pi 2px, pi 2py. So total 10 electrons are present in the bonding molecular orbital. 6 electrons are present in the anti-bonding orbital. Let us locate them. Sigma star 1s is having 2, sigma star 2s is having 2, and pi star 2px and pi star 2py are also having 2 electrons, 1 electron present in each orbital. Now we divided by 2 and then the bond order comes out to be 2, which means that oxygen molecule is having two bonds between them. One is sigma and one is pi. It is paramagnetic in nature. Why? Because it is having 2 unpaired electrons present in it. Nitrogen molecule was diamagnetic in nature because it was having no unpaired electrons. Now we can calculate the bond order, we can comment on the magnetic behavior, we can talk about the bond length of the ions of oxygen in the similar fashion as that of nitrogen. O2 plus ion will be formed by removing the electron from the oxygen molecule. Oxygen was having 16 electron, O2 plus will have the 15 electron. The electron will be removed from which orbital? It will be removed from the highest occupied molecular orbital, and that is pi star 2py. Okay, so if you see the molecular orbital configuration of oxygen plus ion, you will notice that the difference between the two, that is oxygen plus and oxygen molecule, is just the 1 electron, and the 1 electron is not present here in the pi star 2p y orbital. Okay. Now this ion is also paramagnetic in nature, and it is due to the presence of 1 unpaired electron. It is more stable than oxygen molecule. Now why we are saying that it is more stable than oxygen molecule? Because when we calculate the bond order, it comes out to be 2.5. Oxygen's bond order is 2, it is 2.5, so it is more stable than oxygen molecule, and it is paramagnetic similar to the oxygen molecule, but its magnetic moment will be lesser than that of oxygen, because there the magnetic moment is due to 2 electrons, here it is only due to 1 electron. O2 minus ion will have 1 electron more than oxygen molecule, that is it will have 17 electron, and that 17th electron will be added to pi star 2px orbital. Pi star 2px and pi star 2py are having 1 electron each in them, and the 17th electron for oxygen will enter in the pi star 2px orbital. So the pairing will begin. And when we calculate out the bond order for oxygen minus ion, it comes out to be 1.5, which means that it is less stable than oxygen, and it is also paramagnetic in nature because it will contain 1 unpaired electron. This brings us to the end of this lecture. In the next class, we'll take up heteronuclear diatomic molecules. Thank you.